Hey guys.
Oh, yeah.
So, what's up?
Not a lot. Do you know what's happened to Joseph? I haven't seen him in a while.
Joseph is busy with his make school thingies.
Is what?
Yeah. He is currently with the make school uh, things. Uh, yep.
What's make school?
Oh, make school. It's I think so. He has joined in a venture and created online schooling platform with some guys.
All
I'm
right.
not I'm not too sure, but yeah.
Yeah, I just thought I hadn't seen him in about in quite a while.
Yep. He is not currently attending any of the he's totally I think so involved in the stuff.
Yeah.
So today we have to start with TD, temporal difference learning. I was going through the original paper uh, by Rich Sutton on this topic. That is learning to predict by the methods of temporal differences that came out in 1998. 1988, sorry. Uh, uh, it was quite interesting with respect to since TD learning came before Q learning with a kind of a uh, off policy. Q learning was a off policy, and TD, I think so, had a on policy, or which was based on model based out outcomes. So model based learning. Sorry. Uh, it was interesting to see uh, the theoretical foundations of this paper and what uh, 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 how do I say it, those his historical context with respect to the multi-layer connectionist networks that was popular those days. Uh, uh, and how did they took those ideas from that and connected it to the temporal difference and the temporal difference lambda, the TD lambda, with the same examples that is given in this book with the bounded random walks, the random walk example that he gave, and then the next chapters too that was originally presented in this chapter. So, should we start with the reading and the discussion part, or should we allocate some time?
I'm not sure. I've read through it already, so
Okay, okay. If
but I don't know what
yeah,
everybody else is.
yeah.
Yeah,
Uh,
I read it too.
mhm. Yeah. Should we go ahead, Artur? Uh,
Yeah, I'm fine with starting with discussion, but it depends if everybody is fine with it.
what do you say, Terence? Should we start or?
Yeah, I'm fine with that.
Cool. So let's start, and we can catch up in the next part too. Uh, so let me try to share my screen. So uh, firstly, let's give a brief introduction of what temporal difference learning is. It refers to the class of model-free methods which learn by bootstrapping from the current estimate of the value function. And they sample from the MC methods and perform estimates and perform updates that are based on the current estimates, like in the DP methods that we discussed. So the main thing is the main meat of the target here is with respect to the guess of the guess. That's the bootstrap. Uh, and this algorithm was famously applied to create the TD gammon. I think so. We had some sort of a discussion about that in the first or the second lecture. Uh, TD gammon. Oh, let me try to share my screen. Yep. So this was the game that they applied this to, uh, temporal difference learning and a TD camera, and this is where the uh, kind of like the uh, how do I say it, the popularity of this algorithm reached a critical point, uh, and this algorithm in the game of backgammon, with respect to try to uh, quick overview of what this game was. So this was the game. Uh, it's a way like chess and like Go, but with smaller number of states. So uh, these are some of the blacks and white. Or how do I say it? Uh, mm, keys or some I'm unfamiliar with this term uh, of what do they refer to these as, uh, but we have to have some sort of a how do I say it, positional implication in the end that corresponds to the winning state. And I think so here what they did was uh, uh, they learned the moves and were able to beat them in the different environments that they tried their hands on, with completely deterministic, and some sort of stochasticity was also induced, and those kind of a die roll which they did here. Uh, so yeah, this is one of the uh, uh, seminal papers that uh, uh, raised the popularity of temporal difference learning with respect to how many rollouts can they do in a commercial, uh, and the self-learning and the other things. This is a huge. If we continue to discuss this, we can. Uh, how do I say it? We can give our whole 2 hours to this subject with respect to how many intricacies and the framework which had those numbers of uh, computational improvements over the traditional methods. So this is an important milestone or the temporal difference bandwagon, if we say that. But anyways, these are the slides of David Silver on the left of my screen. Uh, yeah. So they, since we have already discussed the DP, the dynamic programming, and the Monte Carlo approaches, uh, we just to give a quick recap of how they had uh, those evaluations. Uh, I think so. Everybody knows that this is a simple value policy from the episodes on the policy pie. So this is a simple state action reward triplet in policy, and this is a simple goal, which, sorry, the return, which is the sum of the discounted rewards. Then the third is the recall that the value function is the expected sum. So this is sorry, the value function that we had. I mistakenly alluded to as the policy, the reply, which is the expectation of the return here. And the Monte Carlo policy evaluation uses the empirical mean returns instead of the expected return, which is calculated as this is a kind of an incremental mean. So this is based on the sequences that can be computed. So x of k is this is the formulation which we do with respect to calculating the mean of the states of the value iterations that we had to do. And this was the formulation which we use for the Monte Carlo updates. The V of ST is V of ST plus this alpha times dt minus V of SST. So yeah, if we go back to the text here, the TD prediction, the first section, they talk about this stuff, and we are only focusing on the policy evaluation. part in this part of the section that we will be discussing, that is 6.1, 6.2, 6.3, and 6.4. Control, I think so, will come around in the later part. So, yep. This is the recap. And then this is the time, and the alpha is the constant step size parameter. We call this a constant alpha MC, constant alpha Monte Carlo methods, which we already know that Monte Carlo must wait until the end of the episode to determine the increment to the state, the value function of that particular state. So because we have to do it based on the uh, g of t, which is, yep, this guy, which can only be which we can only get at the end of the episode. So that's one thing. Yeah, and the contrast with TD methods is that we need to wait only until the next time. At T plus 1, they immediately form a target and make a useful update using the observed reward T plus 1 and the estimate of V of ST T plus 1. And so this is the formulation of the TD method. The V of SST is V of ST plus this guy. The alpha is the uh, uh, step size, and this RT plus gamma of V of state ST plus 1 is given as the TD target, as we will uh, see in the next part. And this guy here, the total RT plus 1 plus this times minus the error that we had, because this can be thought of as a guess of a guess. So this is the TD error, that this whole term is the TD error, and this term is the TD target which we had. So so this difference gives us the error which we iterate upon to build up our convergence to, which to I think so in most of the cases it actually converges faster if we talk about empirical evaluations, as we will see in the next part. But yeah, let's go ahead. Now we will talk about, I think so, yeah, please feel free to jump in if you guys have any thoughts. This is a simple tablet TD0 for estimating the VPI. Since it is episodic, so we only consider the episodic cases here. And the step size is from including 0 to, sorry, excluding 0 to including 1. So, yeah. Then this is a simple loop. Then we initialize as the action, the observations, the VS, which is the meat here, this guy whole of this, and then this is the S prime until the S is terminated. So this, as you can see, for each step of the episode, we are looping and we are updating the value function here with respect to the every step that we get to. Uh, then we can also say that since TD0 bases its update in part of the existing estimate, we say that it's a bootstrapping method like DP. Uh, so this is the definition of the expectations of the return G of T. And from 3.9, we had G of T can be written as this too. And this is the Monte Carlo version, and since it's using the return of the whole of the whole of the return of a particular uh, how to say it, episode, uh, and the here they use the 6.4, which is kind of like a DP method of to calculate the estimate of. So here they, what do they do? Yep. Uh, so with respect to the Monte Carlo estimate and the TD target, the TDA estimate, they say here that uh, the TD target is an estimate for both of these reasons. That the first they give is it samples the expected value and it uses the current estimate instead of the true VPI. So that is the reason here why it's the TD target is an estimate. Mm. And yep, this is the TD methods combine the sampling of the Monte Carlo with the bootstrapping of DP. So this is a very good how do I say it, the explanation or the intuition behind uh, how to understand it and to take for trying to imagine it to solve the future problems with respect to the examples that we will see later. Uh, yep. And in the slides, yep, we can see that it directly learns from the episodes of experience. It's model free. It learns from incomplete episodes by bootstrapping. That's the guess of a guess. Guess towards a guess. And, that's the difference between the incremental every visit Monte Carlo and the temporal difference, which we just alluded to. Since we saw that uh, uh, the TD updates the value towards the estimated return of this guy here. And these, and this is the equation. So it's the same really. But yep, as we had the differences with respect to the return of an episode versus each step. So which we get the estimator. Yep, I already alluded to the TD target and the TD error part of this. So, how do we estimate and how do we recursively compute this across the value states to get a policy with respect to the value iteration parts, and how do we empirically try to uh, uh, evaluate this? Yep, we will see in the next slide. This is a driving home example, but before that, let me get back to how it started. This is a backup drag diagram. As you can see, this is a TD0. That's one step that has been taken. The state, the action that it took, the next state that it arrived to. Yep, do you guys have any queries here? It's straightforward, really. If please ask if you guys have any queries.
Not for me, thanks.
Yeah, cool. Yep, this is simple. This is the update that I described the guess of a guess, which is a kind of an error. As David described it in his talk, so if you take a guess and based on that guess, if you take a second guess and that second guess is towards and you try to evaluate it, and if it's towards the particular uh, 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 convergence function that you're trying to reach, then you update it with respect to the estimate and you try it again for the next step. So that's how it is done. This is the TD error. Uh, which he described it. So this is the estimate, the next state, the next reward, and we won't get it until the one time step later. This is the same thing. Then this is on the left is a MC error that we get, and on the right term, this is the sum of the TD errors that we get. So this can be written as this too. And this del of t is taken from here. It's a simple kind of like trying to sum it all together. Here we have this term being added and subtracted. And yep, this was the original. These three guys. So to get the derivation right, we have used this. This is our sum of the gamma to the power k minus t del of k. So yeah, this can also be written as the sum of the TD errors, and it can be written as this. This 6.6 is just a way of representing the sum of TD errors. Yeah, during each episode, then they empirically define it as how it's not updated during this episode, but the step size is small and then it may hold approximately. That depends, but yep. For the real value, for the real world evaluations, this kind of a error term might have to be uh, bounded based on the parameters of the how do I say it? Uh, uh, the data that we have with respect to the uh, uh, problem that we are trying to solve. Uh, and yeah, we will see in the implementational part uh, what these differences are. Um, how can we generalize it? So let's talk about the exercise 6.1. Here they, here they talk about the redoing the derivation to determine the additional amount that must be added to the sum of the TD errors in order to equal the Monte Carlo error. So this term, what must be added? So uh, there is if we take this as a UK plus one, here is the answer. If I can, we try to, yeah, and here is the derivation. Uh, the additional term that we talked about. Mm, we try to rotate it. So yep, it's simple really. If we have taken this guy as this, and alpha into RT plus 1 gamma VT ST plus 1 minus P VT of SST. So yeah, and we know that from here that this is equals this. Uh, this term is to be added here with respect to this guy. This is simple expansion, and what we have done in this step. And here it's simply the compression with respect to the summation that we have applied from k t to t minus 1. Uh, yeah, this is the term that we get. Yeah. Mm, yep. So I think so. Everyone is clear with the exercise 6.1. Let's get to the example 6.1. This example is uh, we should open this up. Ah, so where? So yeah, this is with respect to the this is the same figure that we had in the book. Uh, this is the constant type, constant step size MC, and this is the one step TD. Uh, and if we take a look at this driving home example. uh, So this is with respect to the estimate. I think so. You guys have read this of what this example is trying to say. Uh, if not, let me uh, uh, please indicate as to whether I should uh, try to quickly give an overview of what they are trying to say with respect to the problem formulation. Here is the problem formulation with respect to the example 6.1. Yep. So I think so. Uh, everybody got it. With respect to the rewards that are being done here, uh, how do we uh, uh, calculate the sorry the how do I say the uh, predicted total time over the sequence. So this is with respect. This is at the end of a episode, and this is with respect to the update in the estimation at each step of the value. So yep, we can see from here what is the changes here. I can give you a brief overview of what they are trying to do here at every step versus the constant step at the end of an episode, and what the error are, what the error is, and what the return is after each step. Uh, it's easy really if we go through the text, you can understand it, but I was thinking we should discuss some pointers that are insightful. I think so. If we put these values on the equation that we got here, this one, this is with respect to the constant step size MCs, and one step TD is here. The tap W method, and yep, we can easily formulate it, uh, calculate it. This is how this graph was uh, uh, iterated upon. Yeah. Other than that, I don't think so. It is this is any difficult. Mm, the difference in the temporal difference, the temporal difference approach here will just try to give the error in uh, each of the time steps with respect to the updation of the estimates. Uh, so what here they talk about is if we um, leave the office and then uh, we face some sort of rain or traffic, uh, or we uh, after exiting a particular highway, if there are certain uh, unforeseen circumstances, then each those unforeseen circumstances will have some sort of a error, that the TD error that we talked about, we alluded to earlier, which is being added to get the estimate of our new time. So it's how things work if we take a look at Google Maps or any sort of a mapping application, and we try to plot a path. Suppose we stop to get gas, so uh, uh, those estimates are automatically, how do I say it, added to it, time, and yeah, and it works in the opposite fashion too. If we get uh, uh, on a highway, and yeah, we have our speed, which uh, was initially predicted to be slow, but due to the traffic conditions, but is now actually high. So yeah, uh, at each step of the traffic, we might uh, uh, go there. And clearly, this also helps in all the cases of uh, trying to back up. Suppose, how do I say it? Initial try to manage the trajectory with respect to the control parameters of a self-driving car or something, like I alluded to in the earlier examples with respect to the safety of a particular system. Uh, yeah, so that is where this applies to. So, other than that, uh, we all already had discussed the algorithm and the ways to do it. Mm, Go to the exercise 6.2. Here they talk about uh, the same driving home examples, and they ask that can you imagine a scenario in which a TD update would be better on average than a Monte Carlo update. We already have discussed it on the safety issue of a particular uh, system. That system can be a robot trying to do a particular task, a self-driving car, or a rocket, or like in SpaceX or so. So yeah, that system can be anything. Hmm. Then they gave a interesting scenario as to if we change our position to a new building and we start from that place, and since we have the value estimates of all the other uh, pathways that we had followed earlier, so can we see why the TD updates are likely to be much better, at least initially in this case? So yeah, that's one reason too. And what is the difference? Yeah.
So in this example, we don't change home, but we change a workplace, right? So
Yep. I think so. We suppose you have lots of experience driving home from work, then you move to a new building and a new parking lot. So this is with respect to moving to a new. I I think so home, because the work will the workplace, the work building will remain the same, but we can move with respect to uh, the home and the parking lot. So I think so. mm, that's what they talk about here.
so we change the like target point, not the starting point.
Yep, yep.
Because I think it's different, the like the comparison of Monte Carlo update and temporal difference update different depending on what you change, right?
Yep, yep. And plus, I think so. This is also will be beneficial with respect to the dynamic kind of like uh, uh, trying to. Yep. As we have uh, uh, alluded to in the various settings in the past too. Yeah, those extensions will always be kind of like much more applicable through the TD versus the MC or the dynamic programming stuff that we had alluded to.
Yeah, so is the important point here from those two graphs, in the one for Monte Carlo, you need to wait until the end of the episode to get the reward. Like that's why the red lines go right to the top, because you have to wait. Whereas in the TD one, you just have to wait to the next episode. And so if part of your episode changes, you can still sort of benefit from the experience you had in the past, because you only need to know sort of the difference between the two steps.
Mm-hmm. Yeah, true.
So and in Monte Carlo approach, we have like kind of stronger updates depending on the outcome, right? And in TD approach, we have kind of this more moderate changes to our estimates. Is it true?
Probably, yeah. Like obviously in the Monte Carlo one, because you've waited until you've actually got the final result, you have a sort of definite value for your return. Whereas with the TD one, you're just waiting until sort of the next episode and sort of estimating the value of the next state by the bootstrapping thing. And so, yeah.
So can we say that Monte Carlo approach overweights kind of in short, like if we have a small number of episodes, right? So in the beginning of training, it kind of overweights our like particular outcomes, it's kind of biased towards our experience too much, right?
Yep. Mathematically, they say that Monte Carlo is optimal, but uh, if we try to estimate it with an empirical result, they come to the point that uh, TD is at least in the tabular settings that they have tried under the problem settings, it's a bit better than the MC uh, uh, estimates that the uh, 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 predictions, the MC predictions that they had. So, yep, and we will see that in the example 6.2. Mm,
Yeah, I just think, like some people, like in life, they judge their actions by their outcome, and sometimes you can do the right things, but get bad outcome, or uh, like oth- uh, otherwise you can do the like make the wrong decisions and get a good outcome. And if we compare temporal difference update and Monte Carlo update, so the Monte Carlo update is more kind of uh, susceptible to this kind of overrating your like experience, uh, like overrating a single experience in the beginning of training, right?
yep, yep. Uh, that depends upon the application to application basis. But yep, uh, as I have here also, I think so. They gave an example with respect to the uh, some applications I think so have very long episodes, so delaying until the end of a episode is too slow. So in that cases, if we try to evaluate from the first step of the value that we are trying to estimate, uh, uh, the starting position or the initial positions uh, here determine those ending trajectories. If we take a look from a Markovian property, in which we have the history of a trajectory that is being taken into account. So, uh, uh, if we talk about the first few time steps that our agent has to interact with the environment, and if we have sufficiently explored our settings, then yep, uh, that might uh, kind of like have a kind of a lower bias if you're trying to find the optimal uh, trajectory. But yeah, uh, that will always depend upon the how do I say it, uh, the current problem in hand, and then the kind of how do I say it, what's the sampling strategy that we applied with respect to uh, 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 the important sampling or per decision, or what's the concentration of our trajectory. So, uh, yep, that that is a factor here too. Cool. So yeah, that was an interesting point. Yep. Yep. In practice, yep, this is what I try to allude to. The TD methods have been found to converge faster than the constant alpha MC methods on the stochastic tasks. And here they define the convenience. with respect to the fixed policy and how do they converge uh, for a constant step size parameter, and what's the stochastic approximation conditions, how if it's kind of like we here only talk about the tabular cases of the algorithm. For the more approximation part, I think so with respect to the uh, tile predictive coding or the course coding examples that I think so we will look at in the future chapters, where they give some sort of a approximation with respect to some uh, coordinates. Uh, how can we uh, traverse through that with respect to this is only in the general sense in the TD0. I mean one step. Uh, then we talk about the n step TD or the TD lambda and the Q lambda approaches to. So yeah, there we will get to know in much more detail about those things. But yeah, this is just a simple uh, advantages that they discuss. Let me try to get back to the slides too. Yeah, or we should discuss this random walk example. Uh, so here, this is a MDP with A, B, C, D, E, uh, 5 states and 2 end states. Um, this is a representation of this guy here. Ah, so here we initialize the left side with a zero point 0.5. These are the true values, if you can see the blue line here. Sorry, the initial, that's the orange, that's the 0 episode. So that has been initialized with the estimate of point 0.5. And this, and this is the true value line. That's the blue line. Yeah, the true value of all the states are 1/6, 2/6, 3/6, 4/6, and 5/6. So here, yep, as you can see here, um, this is the state reward sequence that we give here: C0, B0, C0, D0, and E1. As you can see here, uh, these are MRPs, Markov reward processes without the actions that they have taken. So, so yeah. The right graph shows the empirical RMS error that's averaged over the states. So here we can see a group of MC values that have alpha from 0.01, 0.02, 0.03, 0.04. Uh, and the TD ones which converge much faster, as you can see. Uh, the 0.5s converge at here. Uh, sorry, the 0.05 this is this guy is the 0.01. Sorry, 0.1, and this is 0.15. So this converges the fastest, but uh, uh, it only reaches this guy here. Uh, Let me try to. As you can see here, you can see here, and you can see here. Empirical RMS over the states. Here, if I can, here we start at this point, C, and we go either to the left or right depending upon our how do I say it, one state in each step with equal probability. So as we can see, this is with respect to the 100th. This purple is with respect to the 100th episode. So the true value that we reach, that's the, as you can see, this line, the purple line, this line, that's the closest that it comes up to after 100 episodes. So that's one representation that we can get. The others are the range between uh, the number of episodes which we tried. Yeah. This is note that this is vanilla TD that is being applied here. We do not have a batch update TD0 that has been applied. We do not use batches here. Now, any other queries with respect to the graphs or some sort of queries in trying to understand any part of it?
Yeah, one question here. Do you know if this is for a single like run, or it's averaged across a bunch of runs?
So for the left, it's those estimated values are averaged across, as you can see the lines here. So for the purple, it's for the 100 episodes, and on the right, yep, this is also kind of like averaged for the V init 0.5, and these are the number of walks and episodes. So at the 0th state, it was here. The 20th episode, it was here.
Yeah. I mean, not the number of episodes, but like you do 100 of episodes. Do you like do it a single time, or do you like run it a bunch of times and then average? Because like right now, if I do it a single time, I have like kind of more noisy output, but maybe I have some error, or maybe I need just to, average across the episodes. Well, not the episodes, but also like do the average RMSE for a number of experiments.
Uh, Yep, that's a very good query. Uh, I think so for the figure on the right, uh, we averaged over the state. So, uh, hmm, for the figure on the right, let me try to confirm it. The right graph.
Yeah, there are no mentions of averaging for like number of experiments, so probably it's a single experiment, I guess.
Yep. Hmm.
Does it not say in the bottom of the box there, Ardo, below where Mayank's got the yellow text? Does that answer your question there, where it says it's averaged over the 5 states and averaged over 100 runs?
Yeah, if it's like 100 runs for 100 episodes, would you think it means that? So yeah, because just from my experiments and from the naming, right? So here he names it episodes and walks, right? And here he names it runs. So probably those are different entities, right? And
But
then,
in
then
the
it's kind of
yes,
average
so
across the runs. Okay,
so
yeah,
like
yeah. I guess
yeah,
it
like in the
answers.
left hand graph. So like in the left hand graph, you can see the light blue curve that's been run for 100 episodes, hasn't it? Averaged over 100 episodes. Whereas in the right hand graph, yeah, so like at the end of the x-axis, he's done the same thing. He's run it for 100 episodes, and then he's averaged it over 100 runs of that, I think.
Yeah, yeah.
Mhm.
I think that's how it is. But yeah, I will just do an experiment and I see if my graph match that. Yeah, because for a single episode, I just have more noise and like a lot of variation. But here it looks like those are like much smoother and more consistent. So probably if he averages across the 100 runs, I will try that and see.
Yeah.
Yep, yep. As you can see from the code here too, the loop. Uh, this is the inner loop that calculates the running step size, and this is the number of runs that it had. I think so. We fixed it here as 100 here. Yep, you can see this here. So for each of the alpha values that we have taken, uh, we have ran 100 steps uh, in this loop here, and then we have kind of like averaged it using some this kind of a appended, and
I see.
no, yeah.
Yeah, so thank you. That clarifies things for me.
Yep,
Thanks.
yep. Mm, yep. So just to these guys, the true values, and this is the steps of sizes that we have. This is the dictionary. Okay. Representing of steps. Okay, so now we move on to the exercise 6.3. Here they talk about from the results shown in the left graph of the random walk example. It appears that the first episode results in a change of only the V of A. What does it tell you about what happened in the first episode? Why was only the estimate of this one state changed, and by exactly how much it was changed? So here, uh, I referred to this to confirm my understanding of the terminal state. If we look at the graph, let me try to put in the slides here too. Start with, yep, this one. This one. Yep. So here we have this guy here. Uh, so what they talk about is uh, the estimate and how they changed, and the walk that landed on A. And uh, so here we can see we can uh, un, get a intuitive understanding of because the walk ended on the terminal state on the left of A here. So that's the terminal state that we have tried. Uh, we can calculate the values very easily here with respect to this equation that we had. It's a simple term of the TD0 that we had looked at earlier. We are just substituting the values. Uh, since we know the value of the term is 0, R is 0 here, that's the reward. And since it's the final state, the alpha is 0.1. If we take this guy, uh, since I think so, we only use the step size parameter uh, point one. That's the uh, I think so that was selected here. Yep, the step size parameter point one, and so we get V of A is 0.445. Um, yeah. And similarly, it went the other way as allude to as this guy here, V of E. We can calculate it as, and we will get a result of 5.5.
So in the first update, we only updated value for state A, and we updated it for 0.05, right? As we have alpha of 0.1, and the difference between 0 and 0.5 is 0.5. So we multiply it and get like 0.005 and move the value down by this well. value estimate down by this value, but our other values are not changed, right?
Yeah, I think they don't change because initially all of the other states, everything has like 0.5 to start with. So like initially there's no change because of the fact that the other states have got the same values, and it's only because of the fact that you're going from A to the terminal state that one changes to start with. And then like once A has got a sort of slightly different value, then on the next pass B will change slightly as well.
Yeah, and so if we like initialize it randomly, the dynamics would change because we will kind of
Exactly, yeah.
or not. Yeah. I think even if we initialize it randomly, only a single value will change at the first stage because all the other updates are just a difference between a value which is not changed and reward is 0 everywhere, and all the values are as initialized, right? So we always will update only a single state during the first episode, after the first episode, right?
Yep. We can go either this way, or then the other episode will be to reach the end state. This, this, and this. So here we will get. That's just to. I'm trying to conclude here. 5.5. Yeah. Here it will be 0.45. These two random examples. Uh, we try to calculate based on the expansion of this guy here.
So the next question is about alpha parameter, right?
Yep. Oh, yep. Next query is about the alpha parameter, and do we think that the conclusions about which algorithm would affect the wider range of alpha values were used? If a wider range of alpha values were used, uh, why or why not? Uh, with respect to, I think so. They are talking about both the TD and the uh, those guys. So let me. This is where I have kind of used uh, to initialize my alpha parameters from a range of 0.25 to 0.2 uh, for the TD, and the constant MC alpha is 0.005 to 0.04. So here we can see the differences uh, in the RMSA over the 100 episodes. Uh, mm, yep. So as we have alluded to earlier, this 0 point, which this lies between somewhere here, with it it reaches the lowest point fast, the fastest, the point 2 1. But in the case of, I think so, this was point 1 or point 0.05. 0.05 TD is just yeah, in its own zone. This one, I think so. It's this guy. Yeah. Uh, so we can see from the bunch here that they reach here. So point 0.1, 0.15, and point 0.2. I think so. These are the TD guys. And if we look at this, these are the MC methods here. With respect to these parameters. Yeah, we can try exploring it a bit too, but so we can see in this particular case, in this particular problem settings that we had, this is how we try to reach it. So this is with respect to the fixed value, which should have performed slightly better. Why or why not? So it's kind of like the same. Yeah.
Well, basically, when we increase alpha, we take into account like we put more weight on our recent experience, right? So on the recent outcomes, and so that's why we kind of go down faster with higher alpha here, and then we go up in the so the error goes up because we like put too much weight on the recent experience, and basically we kind of update it too much, right? So our estimates are fluctuating because of the last episode we observed, and it's not it's never like it's never the true value. It's always kind of either shifted to 1 or to 0 because of the outcome, particular outcome, right?
Yep. But yeah, I think that uh, yeah, it depends upon. This is yeah, yes, you're totally right too. Uh, mhm. Cool. So let's move forward to the next exercise, the 6.5. Uh, Here they gave RMS error, uh, the right graph of the random walk example. The RMS error of the TD method seems to go down and then up again, particularly at the high alphas. What could have caused this? Function of how the approximate values were initialized. So if you try to defer the initialization, have that graph here too somewhere. Let me, yep, this is it. Uh, If we take a look at this, here have initialized it as 0. These are the initial sets of alpha values for the TD and the MC. Uh, and then we have initialized it as 0.25, as 0.75 and 1. And we can see that it's approximately the same. The going up with respect to first, kind of like jumping down here. And this guy here. So if we can see this graph, this pattern, and then uh, let's consider for the TD methods first. So if we group them together across all the 4 parameters, or across all the 4 different initializations, uh, this is approximately the same. I think if we take a look at the graph at different points of the walks or the episodes that we had.
Yeah, but it converges to different, like starting value on the y-axis is different for different different initializations, right? And
Yep.
some seem to be kind of better.
Yep. From the initialization perspective, it these start at, I think so, it's 0.75 or something here. Here it's point. That depends upon the initialization. So uh, that's the total thing. I think so. It's 0.25. The 0.25 and the 0.75, it's starting at the same spot, as you can see. For the 0 and the 1, it's like starting at the same spot. So yeah, this this is a sort of a how do I say it? On the y-axis, this is a sort of a correlation uh, with these graphs.
Yeah, yeah, but the values, like the final RMC, is kind of worse compared to what we have in the book and what I'm getting from my runs here in the book, and it comes to around 0.05, right? Even below 0.05 for the best values. And here we see like it's always higher than 0.1, right? So that's quite significant difference.
Yeah, but I think so. Yep, that too. Uh, I mean, that will be apparent because of the different initializations. But I think so. In the query, they talked about the uh, going up and down again with respect to the curve. So if the curve is right, I think what they are alluding to in this example. Uh, yeah, if the curve is right, then uh, uh, mm, how do I say it? I'm lost for words here a bit, but If I talk about the different uh, ways of how of if I talk about the MC methods right now. Uh, Let me take the brown here. So the general pattern which seems to emerge here is this kind, uh, this, and this, and this. So yeah, it first converges to minima, then it tries to tries. So I think so. In this exercise 6.5, they allude to this kind of a approach, and we are just trying to compare the curves here across different initializations. So, I think so. This makes everything clear. Yep. Here we can see there is a bit of a difference in, but this also kind of like is similar in many aspects to the point 25 and the point 75 initialization of the AMC. So uh, cool. Then for the exercise 6.6, uh, we had a random walk example with the true values 1 by 6, 2 by 6, 3 by 6, 4 by 6, and a 5 by 6. Or states A to E describe at least two different ways that these could have been computed. Yeah, we didn't use some sort of a DP or other approaches. We just had TD0 and MC constant L fast. There are other ways to execute the same. So this is which would you guess we actually used and why? Uh, why would we guess? We could already know now. Uh, I'm confused here.
Yeah, so the exact values for the states can be easily obtained by solving simple system of linear equations. So, for example, value of E equals 1 plus, like, not 1, but is 1/2 multiplied by 1 plus value of D. The value of D is half plus multiplied by a value of E plus value of C. And this, so we will have this 5 equations for each state, and that can be like easily solved without any like even without a computer. So probably that's how we can get these true values. But you can imagine some other ways to, like, for example, you can apply dynamic programming to solve it uh, as we learned it in chapter 3 or 4. And yeah, probably you can draw a probabilistic that approach to evaluating different outcome, computing the probabilities of certain outcomes. So we can compute, for example, a probability of getting to different terminal states for each like non-terminal state, and that will also give us exact values, but that would probably involve like more writing as compared to just solving this simple linear system of equations. But
Yep.
it is quite like equivalent, I would say.
I think you can also say that effectively the terminal state on the right has a value of 1 and the terminal state on the left has a value of 0, and because the probability of moving between each state is equal and there's 6 paths in between, you can just divide 1 by 6 for each path, and like by symmetry C has to be 3 over 6 being the midpoint, so you can just divide 1 by 6 and like that's the increment for each step between the 1 and 0.
Yeah, I guess you can just say that like, yeah, but still like to like do it like proper mathematical derivation, you would have to
Yeah,
like compute the probability of ending up in a certain state, right? And it's like quite straightforward for say state C, because it's obviously by symmetry it's equiprobable, right? That we end up at each state, but it's like just from the top of my head, I cannot see these probabilities right away by for say for state B, right? You need to like mentally construct this probability of going to C and coming back, and that would be kind of a bit more involved. But yeah, that's a good intuition about.
Totally agree. Now, let's move on to the optimality of TD0, section 6.3. So here they discuss about the availability of the finite amount of experience. And in this the incremental learning methods with the experience the experience is present and until the method converges upon an answer. So it's kind of a repeated evaluation. Uh, then they give a kind of a experience with respect to collecting all the available experiences. Sorry, it's simple batch updating. Everybody knows this. I'm trying to uh, uh, and like um, start from the first principles, which is not actually required here. Everybody understands what a batch of training data is and uh, how the batch updating works. So, yeah. So under batch updating, TD0 converges deterministically to a single answer that is independent of the step size parameter as long as the alpha is chosen sufficiently small. And for the constant MC, the constant alpha MC method, it also converges, but to a different answer empirically. Yeah. So, and then in the example 6.3, they gave a random walk under the batch updating. Uh, and, let me try to pull up this figure too. 6.2. Yeah, this will be a scene with the value estimates on the y-axis, the walks, and the episodes. So Uh, yeah, this is the figure that I had. So it starts from the 0.5, but yeah, here I initialized it as starting as point 0.5. Here they might have done it is in 0.25, but other than that, the MC methods are they converge slowly as compared to the TTD methods with the same number of oxen episodes. This is for the TD. I have taken the alpha value of 0.002, and for the MC, I've taken the alpha value of 0.001. And they gave the reason uh, uh, for the question. They answer the query which was asked here of that how is it that the batch TD was able to perform better than the optimal method? Uh, this is since the TD is more relevant in the prediction settings, so that's why. Uh, Monte Carlo methods are in uh, 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 kind of like optimal only in a limited way, but TD is optimal in way that is more relevant in predicting returns, as we have alluded to earlier. So, yeah, that is why. So, any queries here? Uh, this also is a very good problem. And the batching, if you guys like to plow through the code, is it 6.3? Let's figure 6.2. So this is with respect to the line graph. This is the batch alpha for TD and the batch alpha for the MC methods. Here we have the constant update with the batch. This is the constant size MC batch method that we have alluded to here. And this is the number of trajectories that it has generated. This is an inner function that is being called here with respect to the number of episodes. Here we since the number of episode I think so is 10, and the number of experiences we range it. Yep. And we batch it according to it to the whole trajectory, summing up the experiences. The number of trajectories that we try to generate. We try to this. So just file. That's the example. I think so. It will take some time with respect to 100 times 5. Yes. Those thirds are kind of like. Yeah, it's kind of like the same. Yeah. There has been no noticeable difference here, but yeah. In this particular tabular settings, I don't think so the number of batches matter uh, with respect to how many times you try to iterate upon a particular batch. If I try to increase the number of batches here, it will also result in the same. Sorry, the number of episodes in a batch. Uh, I did it only for the MC, but yeah. I think so. The trajectories that we are trying to generate are not too different here. So, uh, let's jump on to the. Do you guys have any other inputs to it? Uh, how we can improve it or get some different results based on the experience that we have? So, okay. Moving forward to the example 6.4, you are the uh, predictor, not the predator. Okay. Mm, so yeah, we have the unknown MRP with the following 8 episodes. Uh, uh, Not. Let me pull up the slides. So this is the 8 episodes of experience. It's simply then this is end goal state. This is end, and this is the batch here. What is V of A and V of B? V of A, the V of B we can easily formulate is at 1, 2, 3, 4, 5, 6, 6 by 8, as we can see, because B's have value 1 on the 6 states out of 8. So 6 by 8, yeah, B 3 by 4. So V of B is 3 by 4. Okay, and for if we talk about A, there are two views to look at it, and uh, they talk about the V of A be equal to 3 by 4 too, uh, depending upon the first, how do I say it, the first case in which from A0 to B0, how do they reach? That's the 100% of the cases. Uh, uh, since if it is in A, it will reach B. So, and the B can be either 1 or 0 here. So for if B is 1, then we have 3 by 4. That is 6 by 8. Uh, or if B is uh, 1, then it is, how do I say it? Hmm, if B is 1, then it is, how do I say it? Uh,
Yeah, so here it's just that when you estimate B, you say that it's equal to 3/4. And then if you're using the TD0 update, because B is the next state, you can just also say that A is 3/4 because it's undiscounted. Whereas if you were using Monte Carlo, on Monte Carlo, you would have to like go to the end of the episode. And so like in that case, there's only one state that starts in A. So under Monte Carlo, A is given the value of 0.
Yep, yep, yep. In that case, it will be 0. Yep. Uh, yeah, but uh, okay, the first modeling we can base it on the Markovian properties, in which it will be 3 by 4 on the M. The Monte Carlo will give 0. Yep, totally agree. Yeah.
Yeah. So and like depending on the like underlying uh, generating process, both can be kind of better or worse, right? So we cannot like conclude here which estimate is correct, right? Because like maybe the B outcome is conditioned on A, and if you start on with in A state, and then the outcome of B is always 0, right? It's possible for some setting, or
That's
we
right. Yep.
can like think that B is independent of A, and in that case, uh, we would we can like safely incorporate the value of B into value of A, right? So
Yeah, so yep, here we and the other thing too, we constructed this MDP based on the batch that we had. So that's a very good point too. If we talk about this example in this sense, uh, from this episodes of experience, we constructed this based on that. And those cases for the this is based on the Markovian assumption, and this is based on the MC. This answer. So yeah, yeah, this is good. Uh, in the sense that we can uh, batch. Oh, they get it. Yeah, but with respect to the empirical formulation, both will be better in some cases, uh, like uh, in the practical scenarios, uh, in the value iteration part, if you're trying to focus on that, this will be beneficial. or else if we have some sort of a trajectory with some safety or other properties in which we have to remember the past states, uh, we can tune our uh, how do I say training to reflect this part, the Markovian assumptions. Uh, I think does that make any sense? Uh,
Yeah, so I guess we like later we will learn methods which are more robust to this kind of like uh, so basically you can make more assumptions about your environment and get faster learning if your assumptions are correct. On the other hand, you can make less assumptions, and then
mhm,
you will have a kind of slower learning dynamics,
mhm.
right? But you are more kind of you are free from this like danger to making a wrong assumption.
Hmm, hmm, hmm.
Right?
Yep.
One thing I'm wondering about if there are some heuristics to tune this alpha and initial values. So I run just run a couple of experiments, and it seems to me that initial in that random walk example, initializing with 0.5 yields the best results in terms of final RMSE after 100 episodes. And I wonder if there are some ways to like if there are some heuristics to find good values for alpha and initial value function.
Hmm. What values for the alpha, the initial value functions? Uh,
Or would it be kind of empirical thing? So you try a couple of values and see what works best.
Yep, those fine tuning, and yeah, we can also model our objective function that is based on the step sizes, and we can, uh, I think, with respect to those trajectories and values, uh, we can model our we can tune it with respect to the weightage that we need to give on. Uh, I am not too sure that it can be done or not, but yeah.
Also, I think we can schedule alpha to decay,
Mm-hmm.
and in this way we will both get kind of faster learning in the beginning, and also we will not kind of diverge from that best value as we observed for higher alpha for temporal difference learning in the random walk example. But I guess for that you also make assumptions that you have a stationary process, and yeah, so decaying alpha is bad when your like actual state values drift, right?
Mm, yep. 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 Yep.
Sorry, guys, I'm going to have to drop off here. So
Yep.
um, we're not on next week because of 4th of July, is that right?
Mm, yeah. We will have to take a rain check there. Uh, or we can, if you guys want to, because this chapter will require I was hoping to go through Sarsa 2 today, but yeah, I think we will start with Sarsa next time, because we invested too much time in the exercises, which was kind of like necessary. The objective of this course was to go through everything. But yep. Uh,
I'm not
uh,
American, so I don't care about 4th of July. So
I'm the same. So
okay. Whatever. I will try to post a Slack message there. But if no one objects, then we might go ahead, because we are already behind on schedule. So
yeah, cool.
yeah,
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 I'm up for next Sunday.
cool.
yeah, fine by me as well. So
Yeah.
Yeah.
Uh, Thanks, guys. Other than that, I don't think so. We have much here. This paragraph explains why in batch form TD0 is faster than the Monte Carlo methods. And the certainty equivalence is the estimate. We might touch base upon this and exercise 6.7 next time too.
okay, I'll run along here. I'll hopefully see you next week. Cheers.
Yeah,
Bye.
bye.
Cheers.
Bye.
Bye.
So okay, see you next week then.
Yep. Yep. Just to give a heads up, we have this so slide number 27 in the lecture 4 notes, which we will begin from in the next week. So, yep.
Yeah,
This
okay, cool.
cool. Cool, man. Thanks.